Hi, good morning, everyone. Can you hear me? Yeah, thanks. I put the chat box somewhere. Yeah, thank you very much for coming such early, especially for people who are not in Australia, and Australia is time is quite early. We are still have a number of people coming in, so let's start a few minutes later to wait for more people. If you, in the meanwhile, if you have any questions, it is a good opportunity to put your questions in the chat board. Yeah, and as before, can I ask you to use the chat board as a subject-related question asking and answering forum. Try not to use that for chatting. Hi, Anchen, how are you?
Hi, Jim. I'm good.
Yeah, thank you for coming so early.
No worries.
And as before, please help me to maintain the waiting room, as well as have an eye on the recording. If the recording is interrupted or something happens, let me know. And
Yes,
also, in case when I'm interrupted, please keep the session going.
yes, no problem.
Yeah. So, yeah, I think let me start my screen sharing first. This part. I'm sharing my screen. This is the top. Okay. So as we still have people coming into the room, I think the session is really too early. Also, if you have any comments or suggestions to this subject or the delivery of the subject, please let us know. You can type in the chat box or you can raise your hand and we can have a small chat before we start today's session. Wow, it would be a good opportunity to let me to synchronize my my Blackboard. Okay. So that's good. Excuse me. Yeah, our number is keep growing, so let's still wait for a few minutes. By the way, what is the time at your local time zone? Anyone from like India? Now should be the midnight. Okay, 5 p.m. 30. Thank you very much for coming. Okay, that is very effort. So Ming, you guys from Vietnam. Okay, here we have a people from 6:30, 8:30, same as me. Based on the names in my student list, we have quite a bit of Indian names there. But from your reply, I think this session is pretty too early. I am in Sydney. I'm in Sydney. Here we are 8:30. I see, judging from the number of Indian names in my list, and from your reply that almost every people are from something like Greenwich Mean Time plus 8 or 9 or 10. We don't have people from a time zone when now it's too early. See. Okay, as you are coming, I announce something. Based on some very reasonable suggestion, I think I should give you some opportunities of Q&A after the session. So I think I can extend the time for a little bit because today is a work day. I cannot extend too much. I can extend for half an hour after the session. We do not have any particular topic. You are free to go, but I will stay here for another half an hour. If you have some questions, you can just come and ask me. And also, I want to remind people from this session that I have officially a consultation hour immediately follows the Wednesday session. The Wednesday session was from 3 to 5 p.m. Sydney time. And after that, from 5 to 6 p.m., because that is out of business hour, I'm a little bit free. I offer an hour of consultation after the session. And that session is for everybody, no matter if you are in the Wednesday session or if you are from today, you are free to join. Join the Wednesday session at 6 p.m. Sydney time. It's both, Denzel. I said I offered official office hour after the Wednesday session, and based on the feedback there, I decided to add some unofficial office hour after this session. But because that hasn't been planned, I can allocate only about half an hour of this session. So if you have questions, you can just stay after the lecture. Okay, we are 10 minutes into the class. We just start. So thank you everybody for coming that early, especially if you have made very much effort. And please, if you arrive late today, please just give it a little bit more effort to try to arrive on time next session, because it gives me a little bit of pressure that when I'm seeing the number of students growing and growing, I just start introducing the subject. I think, well, maybe somebody will miss some important thing. I need to repeat it over and over again. That, well, isn't very efficient. But thank you very much. So our today's topic is relatively easy in this whole subject. You may find there are a lot of technical stuff in today's discussion, but it's okay. It's mainly about the details about. Sorry for my voice. It's mainly about the details of the theoretical derivation of the model, and some specific techniques to implement the model in computer software format, especially in Python. So those are details, and I try to go as slow as possible to get everybody a gentle on ramp into this area. So we go exceptionally slow today. Don't worry. Okay, before we start today's main topic, the first plan is look back and review where we are now. In the first lecture, we have discussed what is machine learning, and we happily arrived the conclusion that machine learning could be think as software 2.0, in which you like to use some very clever mechanism to make a machine to program itself rather than program those instructions to execute some task directly. So when it talks to task, we can how to achieve that. So it comes to ultimately to the task. We provide the machine some experience of performing the task previously, and we like the machine to learn some patterns from the experience, and so to improve its performance in future. To do this, we set up 3 conditions. First, there should be data corresponding to the experience. Second, you can expect some pattern in the data pattern, so that those could be learned to help to improve the machine's future performance. And third is informal, mainly economically and feasibility consideration. If we have explicit mathematical or physical description or instructions on how to perform the task, we should turn to the exact measure. So we adopt machine learning when the patterns we would like to extract is not very explicit. We know there is something there could be learned, but we do not know how to describe that exactly. So the take-home points: data, something to be learned, not directly available, needs to be learned. In the second lecture, we discussed, if we have decided to go ahead with machine learning, what is in machine learning? And the take-home points of that lecture include 4 parts. Data, and we have considered data here. We consider a black box mechanism, a black box process, which generates samples according to that experience part. And we want to learn from those samples. And we address a specific problem in this study, the supervised learning, where this we try to capture a specific relationship in the data, how to map from X to Y. For X, we refer to something that we will always be able to observe, and for y, we refer to something that is given to us in the training time, but is unknown in the test time and to be predicted. To set up for that goal, we first need to limit ourselves. Remember that the point here is this is the limiting factor. We try to limit ourselves in a specific set of hypotheses. We hypothesize, we try to guess what is the relationship from x to y. Okay, and we need to limit our imagination. We do not want to just accept any free form of the relationship. We want to keep it specific. We need some format. Okay, so you can think of that as a space and each point in the space, or you can think of that as a set. Each member of the set represents a specific x to y map. Maybe we call that H. To emphasize it's a hypothesis. Well, if you remember last time's example, we have an Excel table. Here is X. We allocate 2 specific cells in the table to represent the range of the hypothesis we want to accept, and how to select those 2 numbers. And in the last lecture, I have acted as a human flash selector. I manually did that. But of course, we need to learn how to automatically do the selection. And that selector is a learning algorithm. Usually the algorithm and the hypothesis are coupled. You are not freely choose whatever algorithm for whatever hypothesis. The coupling might be loose, but it's not arbitrary. For example, if you try to use a scheme of selecting decision tree hypothesis and apply that to the perception we will introduce today, that probably won't work. So those 2 factors are coupled together. When we are learning some machine learning models, usually we learn these 2 parts together. And usually when you read a paper or you read some books, the traditional way of introducing a model is to introduce the hypothesis set first, and then it comes to the natural question. Okay, we have now set up the hypothesis. How to select one given the data? And the selection is, of course, according to some criteria that we call that loss or cost. So that are the main points we have introduced so far. And it naturally comes to the topic of this lecture, this class, in which we will learn our first machine learning model to implement, to realize this framework. Okay, so as usual, before we go, we do a polling. How everybody goes? Are we ready to go? I think we are good. So let's continue. Well, I please remind ourselves last time we have adopted a really awkward way of selecting hypotheses in Excel. Okay, so before I'm trying, because that point, the point itself is really simple. I can give all the point to you in 3 minutes, so we are not in a hurry. Before we get into that point, let's consider what have we done in setting up the two parameters or three parameters, 2 or 3, depends on your understanding, using in the Excel spreadsheet, to use that to classify our data samples. Okay, and truly understand the point that we see that the hypothesis is a limiting factor. So to put it specifically, we want to consider linear model family. We will have a better understanding of what does it mean by linear a little bit later. We first consider this is a model family, and remember that a model family is to limiting ourselves from considering arbitrary, or I just put any relationship between X and Y. Okay, let's have a very specific example of that. Okay, I think maybe I did a creepy job of try to communicate with you that you can book a volunteer code demonstrators role in this lecture from last week's announcement. So if you, I have one people booked, but he or she did not email me following up. So I didn't put a confirmation, but that doesn't matter. What I'm doing is I just copy some example code from, not here, sorry, from our notebook into another service. So the point why I'm not just using Google's Colab is because when you use this service, it allows me and you to work together, collaborate in the code. Of course, the downside of that is this has a very limited computational power. It's a small, a weak computer. I cannot adopt a lot of people in the project. So I use a book-based system. Oh, anyway, if anyone is interested in, you can register a user for free, just for free, in Cocok.com. Okay. If you have a registration, I am now sharing you the project token. And after that, you can join me. Oh dear. You can join me in the demonstration, and I can watch you and help you when you try out the code. I hope that can help, especially if you haven't people, especially without Python programming skills, to get on the subject easily. Okay, so after the registration, let me sharing you my project. Yeah. Mm. Okay. We have some people coming. So I'm copying the token into the chat board. If you want to join with me, and let's do the exploration together. No, you do not need to sign up using UTS email. It's just a personal sign up. And I'm asking you, if you find there are a lot of people have been in, you can just log off and try to follow us using the Colab, because this is a small service. I'm afraid if we have too many people in, we can just blow up the computer. Well, you do a registration here. And after that, when you enter your registration, you will find something like when you enter the service, you will be located somewhere here. And then there is a project invite token. I have just copied a token in the chat board. And if you put my token into your box there, you will be able to get into my project here. Where is that? Here. Okay. I will slowly start. And okay, people start getting in. Okay. It is not essential. It's not essential. It's if we have just too many people in, please just keep out. Sorry for the inconvenience. Guys, can you move your cursors somewhere in the like comment area? Yes, thank you very much. Okay, we prepare our data here. I won't give very specific instructions here. Let's just go quickly through here. We load the ARIS data, and I take the two parts of the ARIS data, and I did the data selection part to take the first two classes and take the first two attributes. So anyway, after my preparation, the data looks like this. So we start from here. So usually in Python, well, that could be generic. When you start with some data, you'd better to first have a look of your data object to understand its like data structure or how many samples you have, stuff like that. Yeah, let us set up a rule. If you want to experiment something, you can create new cells, and here, play here. For example, if I am Junli, so I can create a cell using this little plus symbol, and I put my initials here. So this is my cell. Please respect with each other. Don't mess with me. Okay, so you can do this. How about that? Yeah. Well, given the data objects, we might want to have a look and explore what do we have. So the simplest way to do this is just to, in a notebook, is just to type it and let it go. Well, we can see that we have a table of data samples, and we have 2 attributes in each row of that table. If you remember something about the Python, we can take the first 10 samples and have a look at that. Similarly, we can have a look at the first 10 samples in Y. Okay, so just an exploration. And in the next step, I'd like to plot the data in a figure, so that we reproduce what we have seen in the previous lecture. The simplest plot thing is to import a plot library, call that import matplotlib.py. Scatter. I can scatter all samples of X using its first attribute as one coordinate, and using the other attribute of another attribute. Okay. I think we have just reached the upper limit of people. My kernel has been killed, so maybe please try to stay there for a while. Don't mess the notebook for now. Thank you. If that does not work, I may just need to go back to the Colab. Okay. When I'm asking you to try out, I will let you know. Where's the part? Okay. We just did the plot part. It's looks very similar as what we have seen in the last lecture. And now let's give it a coloring scheme of using the sample classes. Not very surprising. But what I'm going to do is I'm going to do a further simplification. So basically, to show that how a linear model can prevent us from imagining the relationship anyway, I first simplify the problem a little bit more, so much so that because it is very difficult to imagine a relationship anyway on a 2-dimensional space. So instead of considering a 2-dimensional space, I would take 50 locations here and 50 locations here. Okay, and then I will try to figure out the colors or the classes on the or at the 50 by 50 locations. So basically, I quantize the data into these locations just for the exploration of the variety we are facing. Okay, so our data points are included in maybe some of the 2,500 locations. Okay, so those for those data, I will align them in one of the locations. Maybe think of that. So all this belongs to this location, and this belongs to this location, and this location is empty. Is up to our imagination. Okay, so with that processing, so this isn't difficult at all. This is just some technical treatment to put the data points into the locations. With that, we have the data representation like that. Okay, so the gray dots represent the locations where we want to have a decision. And by decision, I mean we want to determine the class of that sample comes from that location. And for the colored ones, it represents that at those locations we have observed the class of the flower. Okay, and of course the task now is to fill up those gray empty dots. So we need to come up with some coloring scheme of how to put colors here. Is a question clear? I hope. Okay, anyway, let me go a little bit further before we do a polling. So we could be pretty sure that here it probably should be a purple class, and here it probably should be a yellow class, right? We could have an agreement on this, and maybe here it is more debatable, and here we perhaps could not have a consensus about that. So that is the challenge we want to address. Now, before we get into our linear family, let's have a look at how many varieties we are facing. Consider this. Two. Guys, can you distinguish how they differ from each other? Or maybe you think they are just the same to each other. Well, in a sense, you are right. They are same to each other, but not to the exact sense. They are not same to each other. For example, for the first dot, this is purple, and the first dot here is yellow. And what is the difference? Well, you can say, well, there is minimal difference, but there is an essential difference. Maybe you have to look into the code to discover that. In the second picture, I have carefully colored all the locations that we have observed its color, so that the coloring or the classification in this picture is 100% accurate or agreeing with our training samples. What is your feeling? If you move back 10 feet and think about that and look at these two pictures specifically, you probably see, well, so what? It looks as useless as the previous one, right? And please remember a mantra we have learned in the introductory to data analytics. What? You need to distinguish the training and the test performance. 100% training performance is nothing. So this, I hope, give us a very initial motivation on why we would need a limiting factor in our construction of the hypothesis, of the possibilities we want to consider. By the way, if you try to consider all the possibilities of coloring the 2,500 locations, how many possibilities are we thinking about? If we color one location, there are two possibilities, 0, 1. If we color two locations, the possibilities are 4. If we coloring 3 locations, the possibilities are 8, so on and so forth. And if we are considering coloring 2,500 locations in Python, the multiplication represents to the power of we are considering these many possibilities. We don't want to consider these many possibilities. And by knowing the color of the data, okay, by knowing the color of the data, we eliminate some possibilities, and knowing one color, knowing one sample, we remove one location for the choice. Knowing 2 samples of the data, we remove 2 colors. So let's try to find how many data samples we have. We have 90. Okay, so let's this represents the choices we will make from given the data points. Okay, this is significantly less than this, but it's useless as well. We do not want to make these choices. We want to limit our choices. So let's have a very intuitive impression about how the linear models can help us. I will implement a linear model using the way that we have been doing in the Excel. I show you the effect first, and then I will introduce. I will slowly give you some explanation of how I have implemented. And where is my, okay. Think about this coloring scheme. You do not need to you do not need to be an expert to appreciate that. Now, when we try to make our decisions by adjusting those parameters of this model, okay, this is a little bit too much, maybe. So this is a different boundary. So the point here is this linearity gives us much less choices of arbitrarily making decisions on the data space. The decision making, the coloring must have some pattern, and that pattern is much more regular than this one. And the advantage of this is that for this stuff, even if you know that this is a completely agreeing with the data, but see, if here, for example, oh, no. If here, I'm telling you, this is some point that has not been observed in the data, and how much confidence would you say? Look, because when we come to the locations, this coloring scheme completely agrees with data. Therefore, I have confidence that when we look at a location that is not in the data, I have some confidence that this will apply. That this will be a valid prediction about the color here. Ask yourself this question. And then we move down a little bit here, asking ourselves the similar question. Maybe here we haven't observed, okay? Well, I know this boundary is not agreeing with the data, but just, well, for your imagination, see, if this boundary is agreeing with some data, okay, for example, if we have some data representing or is well represented by this boundary, then ask yourself, for somewhere I have not observed in my data set, how much confidence I have at this location. Okay. How to achieve this? Simple. The principle is very simple, so much so that the technical point can be delivered in 1 minute. You may often see the a picture representation of the perception model or linear model in general. it has this inputs, and here is the outputs. Okay, so the point is I will compute a number from my and I will make a decision according to the number. And therefore, this number will summarize all the information in the data sample. And the decision making according to that one number turns out to be much regular on the entire space of data. And for the input, here I just draw two inputs here. Let's call them x1 and x2. It is corresponding to the columns of the data table. So you can consider, given a data table, we rotate it to 90 degrees. So it goes this way. Now I have one data sample of x1 and I change the color, x1 at sample 1, x2 at sample 2, and this is one sample, and the second sample is here. This is first sample, and third sample is here. So it goes this way. And you can consider the samples get into the processing pipeline, get processed by generating a number, and the number is used to make a decision about this sample. And of course, the sample corresponds to the locations in the space in the data space. Is you use this to locate in one coordinate, and you use this to locate at another coordinate. So in this way, you form a geometric point of view of the data, and you imagine the application of the model on the location. This is a decision about this. You will color this as one color or the other. So this is a decision making at that location. And for the linear model, how to reach the number? Easy. We give one coefficient to each data attribute. If we do this and make the 0, 1 decisions directly on that data point, it gives us this result. Okay, I think yeah, let's pause for a while and see how things go. Have I delivered that to you smoothly? Okay, take the opportunity to think about that, or maybe I show the blackboard.
Can I ask a quick question?
Yeah.
How do you select your coefficients? So what are you looking for when you're selecting coefficients? Is there a, what's the process there?
I didn't get the question so clear. You mean
the coefficients? So what do you like? How do you get that number? For example, you got 1.5.
That is okay. Thank you very much. I think yeah. Thank you. I'm very happy. I have been successful straight in 4 lectures about this topic. At the exact point, I have motivated people ask the exact question. That is a very good question. Congratulations, you get the point. And the point is how to select those coefficients, right? Okay, yeah. That is the job of A.
Okay.
And here we have done an excellent job. That's so much so that it motivates you automatically tries to learn this by setting up our hypothesis family very well. And of course, the next step is to invent some automatic way to select this, and that will be discussed in the next lecture. When you have a good view of how the entire mechanism and is working and how that could be imagined in a geometric way, well, the learning algorithm will be designed very quickly in the next lecture.
Okay, thank you. Yeah.
Yeah, that is a good question.
Thanks.
But for now, I just randomly pick up some number, and those number could work, could not work. But the point is not how to make them work. We need a foundation here. The point, the foundation we are laying is that if they are working, we want to be confident they will continue working in future. So that is one of the most important part in machine learning. Okay, and this structure, I don't know if that reminds you one action you have done in the introduction to data analytics class. In there, you are using a software called KNIME. So you have something in this arrangement in KNIME. You have some repositories here, right? And you have the nodes. You select, well, this model or that model. When it comes to the decision that I probably want to use that model family, you drag the node to your workflow and you drop it there. The computer have constructed a structure like that for you. So we were looking into what is under the bonnet of employing a data model. Maybe that can give it another angle. Okay, so let's quickly go through our quizzes, because now I have delivered all the important take-home points now. And after the quizzes, hopefully, we have some more minutes. And because I have said I'm still staying here for half an hour, therefore, I hope I can help you with Python specific topics or questions there. Where do I move? For the quiz. So as usual, as I said, for the first 4, previously I said for the first couple of, but we decided for the first 4 weeks, the quiz time limit is quite loose. You can complete the quiz before the Saturday, and I will grade it and publish the result. But I will guide you through the quiz, so you probably won't worry about the points. Okay. But after the census date, you probably want to try to allocate class time. But I think this might be not a very effective communication, because for all the people who are here, you have already successfully made to the class. Okay. The first question, how many parameters in a linear regression model? Well, that's a little bit over the top, but only a very little bit. So a linear regression model is very similar to the example model we are talking here. The only difference is it's simpler. Why? Remember that we have said you compute a number and then do something about the number, such as the decision making. So for a regression model, this something is nothing. You don't do anything. You arrive a number, output the number, because you are expected to predict a number anyway. You just output that number. So it's easy. Okay. So the question is about how many parameters in the model. The parameters of the model that has been trained based on 150,000 training samples. Oh, okay. The point I want to make here is represented by a trap. The trap is this 150,000. This number is useless. Recall this illustration. Okay, we have a data table here. It rotates 90 degrees, and then the samples are in a line getting into the processing pipeline one by one. But the pipeline itself is not affected at all. So however many samples is to be processed, the pipeline is there. It is like maybe traffic light or something. You can consider like some traffic infrastructure, and those samples you consider them as cars. So the infrastructure is there permanently, doesn't care about how many cars getting through. So that model, to be specific, should consist of 10 coefficients. You have x1, x2, x10, coefficients. You take the sum to have the number W1, W10, and which will be clear in the next lecture. Usually you would like to have another, you call that W0, you call that B, you call that whatsoever, C maybe, a number that is the constant to to adjust the baseline of the output. So the answer is 11 here. And well, I show you an example of how the baseline helps. Oh, where is that? Like here, our baseline is basically this guy. This guy served here as a threshold. If you are above this threshold, you are of one class. If you below this, you are another class, right? But a neat mathematical treatment could make us just write it in this way. Then this zero becomes our infrastructure. It never changes. It is a format. It's not something that we want to touch. This becomes this baseline. Okay, but they are the same. This just change the understanding. This does not change the thing that to be understood. Okay. And if you change this, like if you change it to be you change the location of the boundary. Okay. That might maybe too much talk about this small thing. Okay, 11. And the next one, well, maybe it's a bad arrangement. This is more like a preview than a review. So this basically this question asks, if you have the model set up as A equals W0, which is the baseline, plus W1 x1 W2 x2. So let's consider W1 and x1 is the data, and the W2 and the x2 and W0 is the parameter. So the parameter is always one number more than the information, than the number of variables carrying information in the data. So the question is asking, is this value linear with respect to what? By the value is linear, we basically are considering the phenomenon, the behavior of a map. This is very intuitive. If you have a value, if you have your input along this range, and you try to get some output, the output, this is out range, this is in range. Okay. We have 2 points here, and you have the corresponding output. So linearity or non-linearity, it's not about these 2 points. It's about how the mapping from input to output behaves within the range of the input. So if you have a straight line here, this is linear. On the other hand, if you have something like this here, this is non-linear. So there is a mathematical representation of that linearity. It also requires not only interpolate that, you need to also extrapolate. So if the range of input is a multi-dimensional, so this discussion extends to multi-dimensional inputs, and that is very natural. Think about this. This has two-dimensional, okay? This also apply. So you have one dimension for the output. And if you have any 2 points in the input, the corresponding output have such a property, it's linear. So, but the point here is that it's maybe just an argument that the value of A is straight. It is a straight pattern, but it's not strictly linear in X. Why? It invites you, where is that? If you click this choice, it will explain to you. That is because W has one more dimension, so that because the function is computed not only with x1 and x2, it's also with W0, W1, W2. That W0 affects the linearity here. Okay, but that is only a theoretical discussion. You can forgo it for now. But the important delivery here is to remind this is also a function of W1, W2, and W0, and it is linear with respect to W. The right selection is A is linear with respect to W, and it's not linear with respect to X. I won't go too much in the not linear with respect to X part. You need to you can choose a wrong answer and see explanation. The important thing is it is linear with respect to W part. Why? Because think about that. The behavior of the mapping is not exactly the complete behavior of the function. This number, let me go that. This number is not of our much concern. And actually, how we change W and the change of W affects the change of this number is our concern. Remember the question you asked just before, how to choose W? Well, X are given. We cannot do anything about X. They are just the facts. We accept them. What we can change is W. And change W, hopefully change the behavior of the model. So if the output of the model, this relationship, the output of the model and the W is clear, then we are good. We can design learning algorithm stuff. Okay. So choose this one. Question 3, and well, that question is a graphic one, and I'd like invite you to give it a thought. Basically, it asks, if using those, well, one coefficient, another coefficient, therefore my calorie scheme will be a line boundary on the space using this hypothesis, set. Which one's relation in represented by the training data is representable, is capable of being completely distinguished using that hypothesis, which is not distinguished. So you can type your answer in the chat. Can't distinguish D. Yes, thank you. That is very good. And A, okay, anyway, maybe I should ask that clearly. You type what can be or what cannot. But anyway, we have a consensus here. Everybody agrees that we can cut A and B, but we cannot do that for D, right? So summarize. The number of parameters of a model has nothing to do with the number of training samples. Of a linear model has nothing to do with the number of training samples. So this is the answer to the first question is 11. And for the second question, the function A equals W0 plus x1, x2, x1, W1, x2, W2 is linear with respect to W, and it's not linear with respect to X. And question 3, this situation, and this situation can be linearly distinguished, and D is not. Okay, you can submit your quiz and wait for your 3 points. Okay. So in the next few minutes and ongoing into the question 3, A, B, C, you can distinguish A, B, and C. Okay. For the next few minutes and ongoing, I'm trying to demonstrate. We have demonstrated the computation theoretical steps of the computation model, how we can implement that in computer software. Okay, and how about let us adopt a protocol? If you are coming in with me, you type a number 1, 2, 3, 4, depends on your order. If you are the first one, you type 1, and if you find someone else have typed 1, you type 2 in the Zoom chat. When we reach 10 people, don't come in anymore. Anyway, you can please negotiate by yourself. Thank you, Ryan. Ryan 1, okay. Okay, I have reached 9. Maybe we stop here. People who didn't get in, please do not get in anymore. This computer is really small, and basically I buy the service out of my own pocket, so I cannot afford a powerful online service. Sorry about that. So anyway, we consider this construction. specifically this guy. So we try to understand this beast. I go up till we reach our old friend X. Okay. Here, no. Look, this is a good way for you to learn a piece of code. And in Python, if you type 3 quotation marks straight, it means for whatever below me until you reach another triple quotation, all of those is a string. And that string can contain a change of line or any stuff. I use because a string itself is also grammatically legal thing. So people often use that as a comment. This is a very convenient way to comment a piece of code and start it. I have my sample X here. Okay. So as you can see, my sample X record these two brackets here. So it is a 2-dimensional table. It's a table. And for first dimension, it refers to the number of samples, or refers to each of the sample. And for this dimension, it refers to per sample attribute stuff. Okay, you have this represented x1, x2, and when we refer x1, x2, that refers to attributes applying to all samples. And this is individual data sample. Sometimes you call it points. Okay. And in Python, the convention is that you have a collected object, and that collected objects collects what? None other than individual samples. So if you index 1x, it returns you 1 sample. So we can write a for loop of that. Okay. And look, now for each of these, we can see so this is exactly the same. I do not need to explain that too much. Okay, so for now, the X has 2 elements, right? It's easy for, this is just a shortcut. It's easy for us to take the 2 elements out from X to make the process easier. Okay. And then now we are very easy to do something about those X, Y, and X2. But before that, let me clean up my for loop. So instead of with an index, I can directly use elements in the X. I take the first 3 elements. I loop over the first 3. And now I do not need this anymore because I have directly code that in the for loop. Also the same. Okay. I hope people follows me. I don't know. Let me just do this. Okay, you haven't followed me? You can try. And I can also directly take apart that sample in the for loop. So this is just a convenience. When you see similar things in the code, this is the explanation. Don't get confused. So they are just remove some tautology in the description of the logic. Also the same. Well, now we can do something about our X1 and X2. So how about let's call W1 and W2, and let's take. Please, Tom, can you move your cursor a little bit away? Okay. Isn't bad. Keep that in mind. Now I'm doing a very Pythonic magic. So we see, because our ultimate goal is not to print out the H. What if we want to produce the H from X? To do this, we copy this down. We remove the print. We don't need the print. Okay. Look, I want to do this for each H. I just copy that here. Remove this, and I give this a pair of brackets. I print HH. So I keep the one above so you can take some comparison. Look, boom. Done. We can also compare it with something, maybe. Like this. Okay, we can simplify this construction as well. I print that out. for you to know. The simplification is also a bit Pythonic. Prediction equals 1 if h is greater than 5.5, otherwise, sorry, 0, otherwise 1. So this prediction, these are the same. I can just remove this now. Okay, and then I can do this into this. Instead of make it very confusing, I want to give you a step-by-step construction. 0 if this is greater than 5.5, otherwise 1. You can use change of line within any pair of brackets. This is okay, and make the code much more readable. Let's call that PP. Wow, boom. We have done a pretty good implementation, neat implementation of the perception in one line of code. This is really not bad, considering the traditional implementation of the perception, especially the first one. This guy, that was the inventor of the perception, who worked on the algorithm in 1960s. Okay, we are 3 minutes late. So yeah, here is a very quick ramp up. We discussed, using a lot of time to discuss the importance of limiting the choices we want to consider. Therefore, we introduce some regularities in our hypothesis, and the particular regularity we want to discuss today is such a way that we decide that our decisions on each data points depends on a number, and that a number is from giving a coefficient of each input of data, and it can be thought of as you rotate the data table in this way, and then all your data samples now in a line. Those line of sample get into the processing pipeline. Each of them are given an coefficient, and take that coefficient with that data attribute, and take those multiplication result together, those product together, you get one number, and the number is used to color that location in the data space represented by the input sample. We have also discussed how to implement this idea in Python in a very elegant way. Okay, so that is what we are going to discuss. You are free to go. And also, if you have questions, you can stay. And I'm still here for half an hour. I got some very unhappy. Okay, don't be so unhappy, Rohit, because you have 2 times to try the quiz. I have, let me start address the questions. And thank you very much, everybody, for coming. That's a really an early lecture. Okay. Thank you very much. But you can live without explicitly saying thank you in the chat, because I try to read a question from above. I got Adam asks, does W just refer to each coefficient, and then we multiply it to get the color options? That's a good question. Yes, basically the short answer is yes. The longer answer is a little bit subtle, and we will touch it in the next lecture. You remember when we refer to W, in this discussion, I'm deliberately a little bit vague about referring whether the W contains the constant. Okay, so usually we for the convenience of processing and the construction of the math, we would think the W includes both the coefficients and the constant. The constant refers to this guy. Why? Because we want to avoid trouble. You know, mathematicians are always very lazy people. If they can include the one object in one notion, they prefer not to invent new notions. So we really won't like the baseline. What we would like to do is, okay, make it from here. And in this way, you are in lack of attribute, because you have one more attribute from those variables in the data. But if you remember that very clearly, probably not. When I refer the variables in the data, I said variables in the data that carry information. Well, basically, we invent one variable that does not carry information. So let's invent some x0 that doesn't carry any information. So that does not belong to the data table. We just give in our analysis and discussion, we just give it a value 1 everywhere, anywhere. You do not need to put that in your computer memory because you know it. You don't let it waste your memory or something. But just put it the 1. So in this way, you reconciliate the W and X.
You're muted.
Thank you. I have another question. Basically, we select W, but not X. X is fixed. I said that is a correct understanding. Yes. Another question, will we be doing the quizzes the whole semester in this workshop? Yes, in each of the workshop, I will guide you through the quizzes. You are welcome to try that before. Actually, that's a good idea to try that before. So in the future quizzes, I will set up, I take a note. I will set up the trial limit to be 5 times. Well, I tried to make it to be the upper limit to be 5, so that it is convenient for you to try it before class. But we have to have an upper limit. The constant is not the WS put together. It's something like that. Oh wow, it's really dumb. Actually, that variable is called a dummy variable. So the constant sometimes is treated this way. If you consider you have, for example, x1 times 0.5 plus x2 times 1.5 plus 3.0. If you consider this calculation, you can exactly copy that and you give this guy a name, call that x0. That doesn't change anything, but that makes your discussion about x and w much easier later. So it is a clever deed. Code exercise in week 2, do you get answers? Let me have a look. I think the answer should be in the handout. Answers, yes, but explanations, I don't think so. It's just too lengthy to write them out. You need to attend the Q&A sessions and you ask me those questions. Also, our 2 tutors are excellent. If you attend their Q&A sessions, you can discuss those with them. You don't calculate the dummy variable. It's how to think about that. It's just there for our analysis easier. For our well, for easy analysis, whenever you refer to them, you just put a 1 there. And in the computer software implementation, you do not need to explicitly put the dummy variables there. They will be replaced with 1. You consider that as a, well, what to see? Consider that as a cyclist. The dummy variable to us is like the stabilizer when we learn how to ride a bicycle when we were young, to us now when we ride a bicycle. It's a way to construct the skills, but after you have already got there, it's just a conceptual thing. It never really been used. Oh dear, everybody pay attention. We now have a $1 million question. What is the best model for the prediction in stock exchange? Well, that that is an interesting question. It's as far as I know, the financial people are very conservative. They use very simple models, so simple, like linear models, as we discussed here, such as the decision trees, when they really put real money in managing users' portfolio. Because for those, I think you need to consider one important dimension of the model, and I think that applies to real-world applications as well: interpretation. So you need to have your solution accountable, which means when there are losses or there are profits, how to attribute the credits, or how to attribute who need to be held accountable. So for those stuff, you need very interpretable model. When the model have been making decisions, you cannot just an everyday deep learning model. Okay, that deep learning black box just tell me to sell or to buy. You need to say, okay, because the market has moved in this way and the index of that has reached that range so much so that I do this. But on the other hand, people are very actively, of course, because it's about money, in investing how to apply modern artificial intelligence techniques in innovative financial applications. And there are some very nice GitHub repositories called deep learning financial data. If you Google deep learning financial data, you probably arrive some GitHub. You probably arrive some repositories collect a lot of interesting recent advances in this area. What is the best model for predict the lottery? Oh, that is easy. I can show you. In NumPy, you have a module that can help you to generate random numbers. Perhaps this. Okay, takes one argument. That's good. Yes, I was joking, but the random generator is useful. What is the model behind self-driving cars? That is also an excellent question. The short answer is there are a lot. And maybe the second shortest answer could be, think about the challenge. The challenge is probably not drive the car. The challenge is probably to perceive what is around the car and make wise decisions. So I hope you can appreciate the much difficulty any human have devoted to learn to move this 1.5 ton of metal according to our instruction. Is nothing at all for a machine. The machine can control the car to the precise centimeters, right? The important thing for autonomous driving is actually the simplest thing for us. To be aware that, okay, there is a dog there, don't hit, don't run over it. There is a pedestrian here, brake. So this environment perceiving and decision making actually is a much, I won't say easier, but that is comes to the second. To be aware that there are hazards on the road, that is the first most important thing. Okay, and then they adopt one of the most interesting thing in my career, that is let a computer to process image. So if you think about that, an image is none other than a huge array of data. That is why you happen to find there is some image processing guy teaching you machine learning. So what you all need to do is to let the computer to figure out, okay, the red, red, green, and blue here in this. Of course, you can understand, maybe here we have 1,000, here we have 800. So you have 800,000 numbers to crunch, right? And at each location, not numbers, locations, and each location, you have 3 numbers, and those 3 numbers are ranging from 0 to 255. Those are RGB values, we all know. So this comes to 2 million numbers of an image. Okay, and the computer is going to scan maybe in this square. If I take the pixels in this square, it makes a decision whether this is a pedestrian or a car or a van or some drivable surface. And then it takes something here, it takes something here, it scans everywhere of the image using every scale. So it exhaustively take all the possibilities of the regions of the image and take the image contents of the regions and then make decisions about whether there are some interesting or unsafe objects in this area. And it needs to do this for at least 10 times a second. Image frame comes, decision made. Image frame comes, decision made. And it tries to be consistent along the way. So that is basically the most basic component of autonomous driving car. And not every millisecond, maybe that is not important, but at least maybe 10 times a second is necessary. It depends on the situation, of course. Usually you have, even in the human driver, usually you have something like a split second of reaction time. No. The machine learning don't do this. If the machine learning analyze the historical lottery data and it is profitable, then it probably won't a question of machine learning. you should get the law enforcement department to look at those people who made those lottery. Okay, think about that. By definition, lottery is to use some random numbers. If there is some pattern to discover, then the good question is who on earth have made those patterns? Okay, anyway, thank you very much. I think I have to go today because we don't have much more questions. If you have more questions, please put them in the discussion board, and you are welcome to attend my other office hours and our tutors. Thank you very
John?
much.
John, just quickly
Hello?
before you go, can I just
Yeah.
quickly clarify one thing? Next week we go into putting in the right, like how you come to an agreement that the W value is suitable. Is that what you were saying earlier?
Yeah.
That's what we do next week, right?
We will learn a method to compute a W value. Yeah, and we slightly touch the topic that how we can be confident that our method is working, because we will motivate the method from intuition, and at the last we will try to discuss why our intuition is correct.
Okay, cool. All right, thank you.
Okay, bye-bye.